We'll go ahead and get started. We're going to look at Chapter 9. Chapter 9 goes over alkynes. So we're looking at C triple bond C. A lot of the reactions that we'll look at will be very similar to the reactions we saw with the alkenes. Okay, so go back to what you learned before the last exam. You're applying the triple bonds now instead of double bonds. And there'll be some new reactions thrown in as well. Let's go ahead and get started and look at some of those reactions. So like the first thing we do when we look at these different things is look at different ways to make that functional group. Then we'll look at reactions that that functional group can undergo. The first thing we'll do here is look at some different ways of making an alkyne. So alkynes can be prepared by elimination of 2HX, so you need a dihalide, so you need 2 halogens attached to your alkyl halide using a strong base, and there are some examples of strong bases there, KOH or NaNH2. So the generalized reaction for that is you have a dihalide. You treat that with 2 molar equivalents of base to form your triple bond. That is the product that you'd want to show on the exam. The byproducts of this would be 2 molar equivalents of ammonia and 2 molar equivalents, in this case, sodium bromide. Depends on what your counter ion is here. So if we look at the mechanism for this reaction, so let's just look at it. Dihalide. Remember in organic chemistry I told you anytime you have a metal, it's just like having a negative charge on this other thing. So writing NaNH2 is the same thing as writing NH2 minus. Okay, so that's a strong base. So whereas an acid will donate a proton, a base will accept a proton. So it takes off a proton. That's where you get this NH3. These 2 electrons form a pi bond, and it kicks off bromine as the leaving group, so you end up with Br minus, and you've got Na plus a solution, so that's where your NaBr comes from. And you have 2 molar equivalents of your base. So if you add 2 molar equivalents, so your second mole of your base in will take off the other hydrogen, form a triple bond, and kick off your halogen. We'll look at an example of that. This is how you would see the reaction written. You may see a solvent written down here, which would be like NH3. But you look and see where your 2 halogens are, and then you just put triple bond there. And you can do a line structure. I'll go ahead and do a condensed structure. Again, it's just a triple bond in between you where you have the 2 halogens. So that is a way you can make an alkyne. So now let's look at some ways, some reactions that alkynes can undergo. One reaction is halogenation, where you add a halogen to them. So if you use 1 molar equivalent, your addition will take place once. So just like with alkenes, H adds to one side, X adds to the other side, and X adds to the most substituted position. So you get morphological addition just like with alkenes. But this time after it adds to your triple bond, you still have a double bond left. So we can add again. We add 2 halogens to the most substituted position. So an example, let's look at a different example. I'll use HX here. Look at Br2. I will say 2 molar equivalents of Br2. Remember, Br2, bromine adds to both sides, adds to opposite sides. If we have 2 molar equivalents, the addition will take place twice. So I had a bromine to each side of my triple bond and add each side of my double bond. So overall, I'll see 4 bromines add. Look at problems from your textbook, so we'll look at, this is 9-3. So the first one, I have a triple bond. I have 1 pentyne. Says I add 2 molar equivalents of Cl2. So I know chlorine adds both sides of my double bond, and so it's going to do the same thing to a triple bond, even double bond, so then it can add again. So I end up with 4 chlorines adding. The addition will take place once, then it takes place twice. I'll look at B. Now this one, it specifies just 1 equivalent of my HBr. So it's HBr, so I know H adds to one side, bromine adds to the other side, bromine goes to the most substituted position. Where I have my triple bond, I'm going to change that to a double bond. H would add here, bromine to the most substituted position. Again, on C, it specifies one equivalent of HBr. On this one, this carbon's attached to this carbon's attached to one, so this is the most substituted position. That's where the bromine goes. On this one, this carbon's attached to two, this carbon's attached to two, and it's not symmetric, so the bromine could go to either position. So you get a mixture of products. I could draw adding to this carbon, and I could also draw adding to this carbon. The next reaction we're going to look at is hydration of alkynes. So hydration, water, so I'm adding water to my alkyne. So H to one side, OH to the other side. I'm going to use the same reagents or very similar reagents that we saw with alkenes. So to add an OH to the most substituted position of an alkene, we used a mercury 2 catalyst, mercury 2 acetate, followed by sodium borate. Here, it's also going to be a mercury catalyst. So anytime you see the mercury catalyst, it's saying OH, the most substituted position. This time, what's most commonly used is mercury sulfate, in a solution of sulfuric acid. Just like with the other reactions that we saw, we'll do the same thing. To add an OH group to the most substituted, my triple bond will become a double bond. So this is what's known as an enol. Okay, ene because of your C double bond C, all because of your alcohol. That's where the name enol comes from. Now, when you have an enol, it'll undergo this process known as tautomerization. Where the double bond takes a hydrogen off of my OH group, and these two electrons form my pi bond. In this keto form, well, it's called the keto form because it has a ketone, is more stable. So that equilibrium, this reversible reaction, will strongly favor the keto form in most cases. If you have an OH attached to an aromatic ring, that's an OH attached to a C double bond C as well, but the aromatic ring is so stable, it actually favors the enol form and not the keto form. Because it would no longer be aromatic if it broke up the aromaticity of the ring. So this enol is actually an enol intermediate. So overall, what you see, now there may be some questions that ask you to draw the enol intermediate. If you're just drawing the products of this reaction, what you'd want to draw is a C double bond O at the most substituted position. So this is an example of when I use what's known as a terminal alkyne. Okay. A terminal alkyne means that the triple bond is at the end of the chain. So if it's at the end of the chain, then I do have a more substituted carbon and a least substituted carbon. You have an internal alkyne, that's where your triple bond is not at the end, it's within the chain. And then they're always going to be equally substituted. So if it's equally substituted, you'll generally get a mixture of products. Let's look at one of those examples. So here I have an internal alkyne. So as previous problems, that was a terminal alkyne because if the triple bond was on the end. So here, this carbon's attached to 2, this carbon's attached to 2. So my C double bond O could go to either position. So I get a mixture of 2 pentone, 2 pentanone, and 3 pentanone. Hydroboration-oxidation may also be used in the same way to an alkene conversion to add the hydroxyl group to the least substituted position of the double bond, so anti-Markovnikov addition. And again, you see the keto, the enol tautomerized to the keto form, which in this case, it's going to be the least substituted. It'll be an aldehyde if you have an terminal alkyne. Let's look at the terminal alkyne. It's the exact same reagents that we've seen with our alkene conversion. Hydroboration-oxidation adds an OH to the least substituted position. So here's your enol intermediate. And that tautomerizes to your keto form, which in this case is the aldehyde. So you can see the differences between the two. So I started with the same thing, 1-butene. But in this case, since they're not equally substituted, the carbon went to the most substituted position. So I ended up with 2-butanone. Down here went to the least substituted. So I ended up with butanol. Now, if you did that same reaction, the hydroboration-oxidation on this one, that's an internal alkyne, you get the exact same products. Okay, because it goes to the least substituted, but they're equally substituted, so again, you get the mixture. So you only see the difference when you use a terminal alkyne. Let's look at some of the homework problems. Look at 9.4. Is what products would you obtain by hydration of the following alkynes? So if I look at this one, I have alkyne, I have, is that 4-octane? Now they're equal as an internal alkyne, so they're equally substituted. I know I could add to this, make my carbonyl at that first carbon. So you get 4-octanone. And that's the only product I see from this reaction. So why is that? Why doesn't it add to this one? I drew adding here. Why not here? Yeah. And so it does add to that one as well, but it's the exact same thing as this one. So if I add that one, 1, 2, 3, 4, is still 4-octanone. So it adds to both of them. I just see that one product because it's symmetric. But look at B. Now this one's not symmetric, so in this case I would have 2 different products. So I can add to the first carbon or I can add to the second carbon. So in that case, I would get a mixture. If I look at 9-5A, okay, working backwards here, what alkynes would you start with to prepare the following ketones? So I know how I get that from an alkyne. Well, I'd want to use my triple bond in a way where I have a choice to go most substitute or least substitute. So if I put my triple bond between this carbon and this adjacent position, then you could go to either position, they're equally substituted. So if I put my triple bond here, then I'll have a least substitute and a most substitute, and so I can control where it goes and only get one product. So that would be what I would want to do. And I'd want to use the one that goes to most substituted. So the one with the mercury 2 catalyst. Look at B. So I cannot make a terminal alkyne from this. I can only put it between one adjacent position. So one, I get 2 pentanone and 3 pentanone. So in this case, I'd also get that mixture. So if I was trying to make this ketone, if I was trying to make 3 pentanone, I'd have no choice but to use 2 pentyne, or let's see, I do have a choice. Let's look at that. No, it's the same thing. Yeah, putting the triple bond the other way is the exact same thing. So yeah, no choice. And I just have to separate out the two products, separate out the product I wanted from this other product after the reaction was complete. Get one more, let's look at 9-6. Same type of problem. This case, I only have one possible place to put my triple bond because there's only one adjacent position. Now I want to go to the least substituted. So I'd want to use Hydroboration-oxidation. Well, B. So here's my carbonyl. So I know I have to put my triple bond between that and adjacent position. Again, just like with this one, where there's only one possible way to put my triple bond, also here there's only one possible place to put my triple bond. Because this side, there's only one hydrogen. So when I'm putting my triple bond, I have to take away 2 hydrogens. Okay. And so I couldn't put a triple bond there because then I'd have 5 bonds to that carbon. So this is the only possible place I can put my triple bond. And it works out to where now they're equally substituted, but it's symmetric. And so if my carbonyl adds here, the carbonyl adds here, it's the exact same thing. So I do not get a mixture. And since they're equally substituted, I could use either method. We'll look at reduction of alkynes. So this is hydrogenation, also called reduction. I have a triple bond, and just like with alkenes, I use hydrogen with the platinum or palladium catalyst. When you do this reaction, you bubble hydrogen through it, so you can't control just one equivalent of hydrogen this way. So I'll always add twice, and you get your alkane. Now, if you want to stop it at the alkene, you're going to make a triple bond to a double bond. You can't just use 1 molar equivalent of this because of the methods you have to use, but you can use a less active catalyst. Less active catalyst is known as Lindlar's catalyst. Sometimes you may see it called the poison catalyst too. So it's a less active catalyst. The Lindlar's catalyst is a fine divided palladium metal that has been precipitated onto calcium carbonate support and then deactivated by treatment with lead acetate and quinoline. Instead of showing that out, which you could, I just write Lindlar's catalyst. So I've taken 2 butane, react that with hydrogen over platinum catalyst or palladium catalyst. I'll go all the way to my alkane. If I use Lindlar's catalyst, you stop at the double bond and you always see thin addition of your 2 hydrogens. So your hydrogens will add to the same side. Another method to do the same reaction, to stop at your double bond, is to use lithium or sodium and ammonia. So your notes say another method to convert an alkyne to an alkene uses sodium and lithium metal as a reducing agent, liquid ammonia. It should say sodium or lithium metal. You do not use both. The difference is that anti-addition is observed. This should say or lithium. So let's look at the same thing, 2 butane again. I'm going to use lithium. So lithium and ammonia. Ammonia is your proton source. So the other one, the 2 hydrogens added to the same side. And so I ended up with cis-2-butene. In this case, I get trans-2-butene. Anti-addition. So here I had cis-2-butene. If we look at a problem, let's look at 9-8. So it says, using any alkyne needed, how would you prepare the following alkenes? The first one says trans 2-octene. Well, I know I'm going to start with an alkyne. I know my double bond's at 2, so when I draw out my alkyne, I'm going to put my triple bond at 2. 1, 2, 3, 4, 5, 6, 7, 8, 8 carbons, so that's 2-octine. Now I want trans, so that means I want the hydrogens to add to opposite sides. So I'd use the lithium and ammonia, or sodium and ammonia. So there's your trans 2-octene. Cis 3-heptene. So again, it's hep, 7 carbons. I know I'm going to start with an alkyne, so I'm going to put my triple bond at 3. That's 1, 2, 3, 4. I need 3 more carbons. Now I want cis, that means I want my hydrogens to add to the same side. I want to undergo syn addition. So in this case, I'd use H2 and Lindlar's catalyst. The last one says 3-methyl-1-pentene. So where am I? Let's go ahead and draw that bond. Like that. So this is a carbon, this is a carbon. I'm just showing that the bond angle is linear there. You can still draw at an angle if you want to, like that. But sometimes you may see it written like this, where it's showing the actual 180-degree linear bond angle. So you just have to know that this is a carbon, carbon, and then this is a carbon. So in this case, you can't tell if it's cis or trans, because I have 2 hydrogens on this side. So you could use either method, lithium ammonia, or H2 and Lindlar's catalyst. I'll use lithium ammonia just because it's easier to write down. But you could also use Lindlar's catalyst. Another reaction, we saw this reaction with alkenes as well, oxidative cleavage. So ozonolysis or hot acidic potassium permanganate. Remember, ozonolysis was ozone and steam. We see the same thing here. cleaving the triple bond. With ozanolysis, we cleave the triple bond and made a double bond O. We're not going to make a triple bond O, but we are going to have bonds to oxygen to each one of those bonds. So when it cleaves it, it makes a carboxylic acid, just like hot acidic potassium permanganate did with alkenes if you had a hydrogen attached to it. As such, you could also do the hot acidic potassium permanganate and do the exact same thing. So in this case, ozanolysis and hot acidic potassium permanganate both yield the carboxylic acids. And when you have a terminal alkyne, if you have the hydrogen on the end there, you end up with carbon dioxide, just like if you had two hydrogens on the end when you had an alkene with hot acidic potassium permanganate. The last reaction we're going to look at in this chapter, chapter 9, has to do with the hydrogens on the end of a terminal alkyne. So the hydrogens on the end of an alkyne attached to a triple bond are weakly acidic, so they can be removed with a strong base. This only applies to alkynes. This reaction will not work with a double bond. You cannot take the hydrogen off the end of a double bond. You can only do this with the triple bond. So hydrogen attached to a triple bond. So we're going to use a strong base. I'm going to use a strong base that we used before, NaNH2. It forms what's known as an acetylide ion. Then you treat this with some kind of an alkyl halide. And whatever alkyl group you have attached to your halogen will add to the end of my triple bond. So overall, what you would see, usually it's just those written in different steps. NaNH2 followed by, let's make it a little different this time, put an ethyl group. So my NH2 makes a acetylide ion. So I end up seeing is whatever's attached to my halogen now attached to the end of my triple bond. Byproducts. NH3 and NABR. So anytime you see this NaNH2, it's going to usually be applied to something with a triple bond. It's either going to be making a triple bond or taking the hydrogen off the end of a triple bond. So just, you should be able to associate that with the triple bond somehow if you're taking the exam. NaNH2, making a triple bond or taking the hydrogen off the end of a triple bond. Let's look at the mechanism for that. have my strong base. I know this is a strong base, weakly acidic proton, proton donor, proton acceptor, takes off the hydrogen, makes my ion. Now this is stable, relatively stable, and that's why I can lose it, but it's still not very stable, so this is going to be highly reactive. So if I have an alkyl halide, I have a polar covalent bond, electrons are being pulled towards the bromine, so partial positive charge here, that negatives attracts that partial positive. And I add the alkyl group on the end. So you kind of see where the NH3 comes from as a byproduct. Here the NH3 is forming. Here I'm kicking off Br minus, and I have sodium ions floating around solution, so that's where the NaBr comes from. Now this reaction has a limitation that your alkyl halide that you use here has to be either a methyl group or primary. Okay. It won't work with a secondary halide or a tertiary halide, and we'll talk about exactly why it will not work in chapter 11 when we get to chapter 11. The reason is that it favors elimination, it favors forming a double bond instead of substituting on instead. So this leads us to another type of problem that we'll encounter in organic chemistry that you'll see on exams. So some of the types of problems you see are nomenclature, where you have to name, you're given the structure, you have to provide the name. Or you may have to, given the name, draw out the structure. And then we've seen problems where you have a reaction, so you're given the starting material and these reagents, what's the product of that reaction? Or we may see problems where you're given this product, how did you get that product in one step? Or you see mechanism problems like this, using the arrows to show the electron flow in our chemical reaction. So another type of problem is what's known as an organic synthesis problem. So organic synthesis problem is you want to make this compound and you're given from this other compound, but you can't do it in a single step. And so it's like you want to start with A and make D, but you can't go directly from A to D. You first have to make B, then you have to make C before you get to D. And so it's multiple steps in this organic synthesis problem. And so this is good practical applications for like the pharmaceutical industry. If you're making a certain pharmaceutical, you want to see what starting materials you can start with, and there may be some research being done to make some pharmaceutical. It takes 11 steps, or there's work being done to where you can shorten it down to 8 steps or something like that, so you get more yield. Sometimes organic synthesis trying to make a compound in academic labs is just used for the intellectual challenge. So a lot of times at universities, you may see people trying to make a compound just to show that, you can make this compound through this method, and it could be applied to other things, but whatever you made may not even have any practical applications to it, like it would in like the pharmaceutical industry or the chemical industry if you're making some certain compound. But in the classroom in organic chemistry, we use these types of problems to test your problem solving skills. So a lot of you going on to medical school or dental school or something, you're probably not going to need to know how to add a alkyl group to the end of a triple bond, but the medical schools and things like that can often look at organic chemistry as, okay, do they have the problem solving skills where they can take these abstract concepts, and apply them, so that it really tests your problem solving skills. And that's what these organic synthesis problems do as well. They look at your problem solving skills. So it's like you're learning this new language, and then can you apply that new language? And that'll be useful. Your problem solving skills is what's really going to be useful in a future career in professional school. And it also helps me to see how well you know the reactions and stuff. Let's look at some more problems from homework. So look at 9-10 first. And so it says, show the terminal alkyne and alkyl halide from which the following products can be obtained. If two routes look feasible, list both. So I have my triple bond there. So I have two different possibilities. I can take off this alkyl group, let's say NaNH2, and then I want to add my methyl group. I could have also taken off the hydrogen from the other end of my triple bond. And then I'd want to add 3 carbons, so that's why I make my alkyl halide. I want to add the CH2, CH2, CH2. So where it's attaching to my triple bond, I put my halogen. Now on this one, I want to check. So this is a methyl halide. This is a primary halide. And so they both would work. Methyl would work a little bit better, but they both would work. So let's look at the next one. Let's look at B. Again, I'm giving my triple bond. So I'm going to take the hydrogen off the end, so I'm going to take it off this end first. So I took it off that end and put a hydrogen there. So that means I need CH3CH2Br as a alkyl halide. I could have also taken it off the other end. So I took this part off and replaced it with the hydrogen. So again, NaNH2 takes off the hydrogen. So where it's attached to my triple bond, I'd put that attached to a halogen. But now if I look at this, This one's primary. This one's secondary. Remember, it only works for primary and methyl halides. And so I would not use that method. I would only use that one. So again, I'll look and see where my triple bond is. I can take a group off the end of my triple bond and place the hydrogen. So in this case, I'm going to add the methyl group. I could do it the other way as well. I took off the other side. Then I'd have to add a ring to my end of my triple bond. Here, methyl group, secondary halide. Again, the methyl group would work, methyl and primary. Secondary would not work. So only one possibility there as well. 9-11 starts us into the realm of organic synthesis, where I may have to use more than one step. So let's go ahead and look at 9-11. It says, how would you prepare cis-2-butene starting from propine So how would I prepare cis-2-butene starting from propine, an alkyl halide, and any other reagents needed? This problem can't be worked in a single step. You'll have to carry out more than one reaction. So the first thing we'll look at is differences between your starting materials and products, so you can figure out what reactions you'll need to do. And so what's different between the starting material and the product?
Triple bond, double bond.
Okay, so here I have a triple bond. So I have a triple bond going to a double bond. What else do I have? What else is different?
Another substitute.
Yeah, there's another carbon added. I went from 3 carbons to 4 carbons. So if I think about this triple bond to a double bond, we've looked at ways to do that today.
H2 Lindlar.
Yeah,
Cis.
H2 and Lindlars makes cis. And 3 carbons to 4 carbons, we just looked at a way to do that. Okay. Now it's very important the order you do them in. Because if I make this into a double bond first, okay, you can't take the hydrogen off the end of a double bond. You can only do that in triple bonds. So you have to add your carbon first. Okay. So I'm going to add my carbon first. Now I can add hydrogens to both sides and add to the same side. So H2 and Lindlar's catalyst. We finished up class by working a few of the ones on 9-12. It says beginning with 4-octane as your only source of carbon using any inorganic reagents necessary. How would you synthesize a polymeric compound? Well, the first one's 4-octane to cis-4-octene, so you're just going from a triple bond to a double bond, and you're adding hydrogen to the same side. So that one can be worked in a single step. H2 and Linmar's catalyst. Let's look at B. I'll do 4-octane and go to butanol. So what are my differences between my starting material and my product?
Triple bond.
I have a triple bond and want to go to an aldehyde. What else is different?
4 less.
Yeah, I have 8 carbons. In the product I have 4 carbons. So if I have 8 carbons, how can I get to 4 carbons?
Break it in half.
Okay, how can you break it in half?
BH3.
What is it?
Or
That adds an
since
OH
you're going
group.
to make an aldehyde, isn't it? Would you use BH3? Sort of cut it in half.
If you use BH3, just add the carbonyl there, though. What do we use to cleave a bond?
O3.
Yeah, ozonolysis. So we're going to use ozonolysis. But if I cleave my triple bond, if I use ozonolysis on this, I end up with a carboxylic acid because it's a triple bond. And so that would be the answer to F, butanoic acid. I want to stop at the, I want it to be the aldehyde. I don't want to make a carboxylic acid. So what I could do is first make my double bond. Okay. If I use lithium ammonia or H2 and Linmar's catalyst. Now, if I use ozonolysis, those hydrogens will stay there. And I'll end up with my butanol. Let's look at one from look at 9-13. Let's look at C. So I'll make hexanal. So I'll start with acetylene. Acetylene is your simplest alkyne. I'll make hexanal. So again, differences here. Two carbons, 6 carbons, triple bond, double bond. Well, I can add 4 carbons. So let's go ahead and do that. 1, 2, 3, 4. Okay, there's 1, 2. So I'm adding 4 carbons to the end, and it's primary, so that works. Okay, 4 carbons to the end. Now I want to add a double bond O, so what we saw today, we could add a double bond O using the same way we add OH groups. And I wanted to add to the least substituted position. So here's where I'd use the Hydroboration-oxidation, BH3. Get that carbonyl to aldehyde at the least substituted position. We'll go ahead and stop there. We'll look at and that's it for chapter 9. We'll start looking at the chapter 10 next time.